Hey, hello everyone. Good to see you. Good to see you all. Just a heads up, there's no webinar next week. Okay, so next week there's no webinar. However, this week, yes, we do. I think I have done 2 webinars on circular motion last year, and I've done all the easy ones. I've done all the easy problems. So I'm going to go through some more challenging problems today. And we're going to start with 2 that were left from the previous webinar that I didn't finish. Okay, and so hopefully I will shine some light. So once again, we are doing a webinar on the harder side today. So if you're not confident with circular motion, I advise you to watch the last year's webinar instead, and then watch the recording of this webinar. Because if you're completely new to circular motion and you don't understand it, it might be complicated. Anyways. Let's go. So we have if you need the link for last year's webinars, I'm happy to send it to you, but I assume everyone knows where to find them. So yes, webinar 03, circular motion part 2. So problem 1, a car is traveling around a bend of radius 200 meters. The coefficient of friction is 0.1. What is the maximum safe speed? It's quite a straightforward problem. So you have a bend in the road. So the car is traveling. The car is traveling like this at the beginning. Now, if there's not enough grip, the car would travel in a straight line. Instead of traveling in a circle of radius r, the car would just slide off the track, slide off the road. I assume everyone can hear me okay. Yeah, so therefore we need a centripetal force. Now, as I have mentioned, the centripetal force is not some magical fairy tale force. It's a real force. It's an actual real force. So which force provides the centripetal force here? Which force causes the car to turn? Yeah, the friction. Well done. It is the friction. Okay, so there's a friction force. So when the car is traveling like this, velocity, there's a friction force. Friction force towards the center, and that provides the centripetal acceleration. So we write Newton's second law, ma, equals the resultant force. And since there's only one force, which is the friction force, we can write mv squared over r is equal to the friction force. But the friction force, as we know, is mu n, where n is the normal force. That's the maximum value of friction. So let's put it this way, is equal to the friction force of friction, which is less than or equal to mu n, the friction coefficient times n. Therefore, mv squared over r is less than or equal mu n, and n is equal to mg, so which is mu mg. So the mass cancels out, and you have v squared is less than or equal to mu g r. So the velocity of the car must be less than or equal to square root of mu g r. So if the speed of the car is less than that, the car will stay on the track. If the car is more than that, it will slide off the track. So what we have here is we have to say that velocity, the maximum velocity, is equal to square root of mu g r, which is 0.1 times 10 times r, which is 200, which is square root of 200 is about 14.1 meters a second, if my calculations are correct. Yeah, 14.1 meters per second. The square root of 200, that's about 14. Okay, so that's that. Now, this is with an unbanked road. Does everyone understand this solution? How well do you understand on a scale of 0 to 10? Okay, very good. Now, if the road is banked, do you think it's going to be more or less? Let's check your understanding. If the road is banked, more, of course. If you look at a banked racetrack, obviously the cars can go faster around this bend. So for example, this racetrack is banked. It's looks like a NASCAR racetrack, right? And this is a banked one. High velocity allowed as the component of centripetal force across the road will be reduced, and the component of G will be down the track. Well, some of this is correct, and some of it is not. So let's see what you're saying, Alex. You're saying that the centripetal force, and we know that the centripetal force is mass velocity squared over r. Now, so the radius of the curve hasn't changed, the mass of the car hasn't changed, and but the velocity, we're saying that you can travel at a higher velocity. So the centripetal force has increased. If V is increased, the centripetal force is increased. So the centripetal force across the road won't be reduced. Well, oh, you mean parallel to the road? Sort of, yeah. Okay, fair enough. You could argue that way. Okay. So we need to see which forces. So previously, what forces are acting on the car? Well, we have the force which is like this. This is the friction force of friction. And then there's the normal reaction force. Normal reaction force on the car. And then there's the mg, of course. Mg. Mg of the car. So looking at these three forces, we need to draw them. So we have the friction force, the mg force, and the normal reaction force. So we need to split the mg and the N force, sorry, the friction force of friction force. Okay, for simplicity, we will assume that it is at the point of sliding. So the friction force is going to be mu N, and this is N. Because otherwise it just gets too complicated with all the less than or equal to. I hope you understand that I'm just saying this because it's at the point of sliding, because we're looking for the maximum possible speed. So we're looking at the point of sliding. So we have splitting this into components. And we're splitting this into components. Okay, let's make it different color. Splitting this into components. So we're saying this is N. This is 10 degrees, of course. So this is N cos 10. This is N sine 10. This is mu N sine 10. And this is mu N cos 10. So the forces, it's accelerating this way. Yes. So vertically they're balanced because it's not going up or down. It's just moving in a circle. So horizontally, it's accelerating. It's accelerating to the left. The acceleration of this car is towards the center of the loop of the circle. Therefore, the acceleration is going to go left. Right, this way. The acceleration is this way. And we use the same thing. So mass times acceleration is equal to all the forces acting in this direction. So it's going to be N sine 10 plus mu N cos 10. Now everything would be perfect if N was mg, but N is not mg because we need to look at the vertical forces as well. Vertical forces, we have N cos 10 minus mu N sine 10 equal plus mg. This is the vertical forces. So from here we can take N, I guess. We can take N to substitute into here. So from here we have N cos 10 minus mu sine 10 equals mg. So we have N is equal to mg divided by cos 10 minus mu sine 10. So we have N. Now we substitute that N into here. So, and this is V squared. So mv squared over R is equal to N, which is mg over cos 10 minus mu sine 10 times sine 10 plus mu N, so mu multiplied by mg multiplied by cos 10 divided by cos, well, it's the same denominator, so you're just going to join them together. Okay. I might have made it slightly more complicated than I had to. Okay. And now M cancels. And you have V squared is equal to R multiplied by G multiplied by sine 10 plus mu cos 10 divided by cos 10 minus mu sine 10. All right, so V is equal to square root of that. And as you can see, it's a similar expression. We had mu gr, and here we have this gr. So square root of sine 10 plus mu cos 10 divided by cos 10 minus mu sine 10 rg. And the previous one, I just remind you, it was square root of mu gr. So similar, yeah? In a way, these are similar answers. You just need to just calculate it. And so sine 10, I think, don't forget to switch to degrees. Square root of sine 10 plus 0.1 times cos 10 square bracket over cos 10 minus 0.1 times sine 10 multiplied by 2. Is it 200? Yes, multiplied by 10 and square root of that. 23.7. So you can see this is a quite a dramatic increase. With only 10 degrees bank, you can travel at a much higher speed, 23.7 meters per second. Now, here I said that n is mg over this thing. What would happen? How far would I be off if I just assume that n is mg? Obviously, it is not, but it might be very close. Assuming n is approximately mg. Does that make a difference? So in that case, you would have ma. So from here, you take this bit. So ma equals mg sine 10 plus mu mg cos 10. M cancels. We have v squared over r is equal to g sine 10 plus mu g cos 10. So v is equal to square root of rg, open bracket, sine 10 plus mu cos 10. And as you can see, it's very similar. It's very similar, just without the cos 10 minus mu sine 10. Let's see what this gives us. So square root 200 times 10 times open bracket sine 10 plus 0.1 times cos 10 close bracket 23.3. So you see it's 23.3. So we wouldn't be very far off. So this is not a dramatic assumption. I mean, why is n not equal to mg cos 10? Why would it be? Why would it be equal to mg cos 10? You have, if the vertical forces have to be balanced, so you have the vertical forces are equal to the horizontal forces. Newton's first law. This force plus and this force and this force, they have to be balanced. So mg plus mu n sine 10 is equal to n cos 10. And you can work out n from this equation. Does that make sense, Ben? Okay. All right. So how did you find this question? How, on a scale of 0 to 10, how did you understand it? Did you understand? So B so is 23.7 meters per second. I think the hardest part about this question is doing this, because everything else is just, well, simultaneous equations. Okay, that's good. I'm very pleased to see lots of tens, 8s, and 9s. That's really good. Okay, so so Andre, do you have any questions? Is there anything in particular that you didn't understand? Couldn't you resolve along the vector of the resultant reaction force? Well, you could, but then you would have two components for the acceleration, which makes it harder. Your acceleration is strictly horizontal. Therefore, I chose this direction to resolve, because otherwise you'll get a bad time with two different accelerations. So, okay, Andre, like nothing in particular, but just the whole thing. Like, do you understand the force diagram? Like, as long as you understand the force diagram and how to resolve the forces, then you're good to go, because everything else is just doing some maths. Right. So the vertical forces are balanced. So that's the vertical. And this is the horizontal. Horizontal. And this is like the key. This is the key to this question, because as long as you can write this, everything else becomes well, easy. All right. By easy, I mean a computer can do it, right? It's very difficult for a computer to do this, but this is like elementary. It's just simultaneous equations. Okay. Problem 2. What is the minimum speed? What is the minimum speed to launch a mass so it makes a complete vertical loop? A, if the object is attached to a rigid rod, and B, if the object is attached to a light string. Okay. So what is that? What on earth are we talking about? So we have a rod and a mass attached to the rod. It's a very light rod. And if we push this thing hard enough, the rod is allowed to move in circles, and it will travel and make a complete loop and return to the original position. Well, if the length of the rod is L, and it's a rigid rod, what's the minimum speed? Can somebody help me? What's the minimum speed you need for it to make a complete loop? So A, rigid rod. What's the speed? What's the minimum possible speed of the ball at the top? Yeah, 0. Because as long as it reaches the top, it can slide down. So at the top, velocity is 0. Okay, therefore, we use conservation of energy, and Alex, I think you are correct. Root 4 mglr. I think so, yeah. So kinetic energy at the bottom. So kinetic energy at the bottom is equal to gravitational potential energy at the top. And therefore, 1/2 mv squared is equal to, well, let's call it, yeah, that's fine. 1/2 mv squared is 1/2 mu squared. Let's call it initial velocity. So initial velocity, 1/2 mu squared is equal to 2 mg L, because the height is 2L, yeah? The height is 2L, and the gravitational potential is 2 mgl. So, and then m cancels, and you have U is equal to square root of 4gl. Very good. Okay, very close, Alex. Just the mass shouldn't be there. So it's a light. That's important. It's a light rigid rod. Light rigid rod. Okay, with the string. With the string, it's a light string. With the light string, it's a little bit more complicated because at the top, it cannot have 0 velocity. Because if at the top it has 0 velocity, it will just fall down, as I shall demonstrate. Skate park. I'm going to use this again today, so if I want the skateboarder to make a whole loop, and let's say I let go from 6 meters, and the top of the loop is also 6 meters. So it should reach the top. It should reach the top. Once again, reaches the top, then slides down. So all I need is I need to release slightly higher. Yes. Makes perfect sense. Now, the issue that we have the stick to track option. So basically, it's like a rigid rod. This is the rigid rod bit. If it's a string, then it doesn't stick to the track. And let's see what happens if I release it at this height. It falls down. Okay. And you can see it reaches the same height. Well, actually, it doesn't reach the same height. No, it doesn't, because it's still moving horizontally. So reaches, and here it loses the contact with it. So this is what happens if you try to spin a mass on a rope too slowly, it will fall. So with a light string, you have to spin it faster. It has to go faster. So at the top, does it take another route to get over the top, overcoming G? Yes, I think you're right. I think your calculation is correct. It's another route GL. With the light string at the top, you have to have enough speed. You have to have enough. Well, what is the minimum speed at the top? Oh, first of all, when you're at the top, you have two forces acting on you. You have the tension in the string, and you have the mg. And these two forces provide you with the centripetal acceleration, because the centripetal, ma centripetal, the centripetal force, is equal to mg plus the tension in the string. That means mv squared over r, and r is the length of the string, so L, mv squared over L is equal to mg plus t. But if you are talking about you need to barely make it, so at the top, the string is going to be slack. String becomes momentarily slack at the top. That's the minimum. That indicates you have the minimum speed. So basically, you lose the tension. There's no tension in the string at the highest point. And this is what happens. So t is 0. So t is 0. Therefore, mv squared over L is equal to mg. M cancels, and you have the speed at the top is equal to root lg. That's the minimal speed you need to have at the top for it to actually travel through. And yeah, you have, so the kinetic energy at the top plus gravitational potential energy at the top is equal to the kinetic energy at the bottom. Therefore, kinetic energy at the top is 1/2 mv squared plus, what if g is 0? Well, then you need 0 speed. That's an interesting one. That's an interesting world. But yeah, you need a 0. You need a 0. A 0 speed won't suffice. I'm just wondering. It just won't just go infinitely slow. Gravitational potential energy at the top is 2 mgl, and kinetic energy at the bottom is 1/2 mu squared. M cancels as usual, as it always does in energy, as it mostly does in energy questions. Multiply by 2, so v squared is equal to 4gl equals u squared. So that's plus, sorry. So u is equal to square root of v squared plus 4gl. And v squared is lg, so it's going to be square root of lg plus 4gl, and that's going to be 5lg, square root of 5lg. And that's a higher speed than square root of 4lg. So as Alex, well done, you did say that it's an extra lg to go over the top. Very good. Perfect. Actually, problem 4 it's the same question as the one I've did. So let's do problem 4 and 5 first, and then go to problem 3, because problem 3 is particularly difficult. Oh, at least to me, from my point of view. A Hot Wheels car makes a loop. What is the minimum height? What is the minimum height it should be released? What is the minimum height it should be released from? This is, by the way, the biggest Hot Wheels slide in the world, and you can see a human for scale, not the biggest human in the world, but a human, and you can see that it is quite big. Height equal to the top of the loop. Well, does it? So are you saying that we can, if we release it from here, it will make the loop? Oh, let's test. We have the skateboarding dog. So let's make the top of the loop. Let's make it 6 meters. Exactly 6 meters. And the dog we release from exactly 6 meters. Okay, let go. I don't think this is what you want. Car flying upside down and crashing into the track. That's not complete the loop. Lucky, do you understand? Do you understand why it's not that? This height, Serena, from the height which has the same GPE as kinetic energy for the minimum energy. Well, that's also wouldn't be true because you have the minimum kinetic energy. You forgot that you have GPE at the top as well. So we first of all we need to work out what's the minimum speed at the top. So we have a car at the top. It's a Hot Wheels car at the top, and there are forces acting on it. So the forces are normal reaction force, which is down, normal reaction force, and mg. So let's draw this. We have N and we have mg. And these two forces provide the centripetal force. So MA centripetal force is equal to normal force plus mg. And because we're traveling at the minimum possible speed, it will be losing contact with the track. At minimum speed, the car loses contact momentarily. So at the very top point, we just lose contact with the car, with the track. And losing contact with the track, normal reaction force is also known as the normal contact force. If we lose contact force, that means we lose normal force. And that means normal force is 0. So N is 0. Yes, it is the same. It is root GR. So mv squared over r is equal to mg. And m cancels, and v is root rg. That's the minimum speed that we need in order for it to make the loop. And it is, Pratham. Well done. And then you just need to calculate. So we have so this is this is the minimum, and we have to go. Oh, we're going to go somewhere here. So let's call it H. So we have gravitational potential energy at the top has to equal at the start is equal to the gravitational potential energy at the top of the loop, plus the kinetic energy at the top of the loop. I hope that makes sense. So mgh is equal to gravitational potential energy at the top, so 2 mgr plus the kinetic energy, which is 1/2 mv squared, which is equal to mgr plus 1/2 m rg. You see, because I've put that in here, and that makes 5/2 mrg. So mg cancels, and you have h is equal to 5/2 r, 2.5 radii. Let's check. Well, we need to make the radius fairly constant in order to. So the radius of the loop let's make the radius of the loop is 3. So we need 2.5 times 3. So the radius of the loop is, so this might not work because it's not a perfect circle, but hopefully it does. So the radius of the loop is 3. The radius of the loop is 3, and 3 times 2.5. 2.5 times 3, that's 7.5. So we need to release the skater from 7.5 meters. So fingers crossed. Start. Almost. Just need to reduce the radius slightly. Okay, let's see. Beautiful. Pass. Okay, yeah, I've tweaked the radius slightly, but I mean, I can't make a perfect circle, or can I? Yeah. So let's see if I release the skater from a lower point. So let's say 6.5. From 6.5, it shouldn't make it. Yes, you have loss of contact here. And from 7, it might make it from 7 because the radius here is smaller, but let's see what happens. Yeah. Oh, no, no. Oh, lost contact. So yeah, 7.5. 7.5 as predicted by the model. Quite cool. That's so satisfying. Okay. Right. So that is an interesting feature. This is a very popular question. They really like to ask this question in university interviews. So if you find yourself, but how can we find where on the loop the dog falls off? No, there is a way you can work it out. It's just not an easy. Oh, actually, we are going to do this in problem 5. Not this particular one, but a very similar one. Okay, so Hot Wheels car. It's the same thing. So let's take the Hot Wheels car again. What am I doing? Copy. Hot Wheels car is released from the minimum possible height. What is the acceleration when the velocity is vertical? At what height is the normal reaction 100%, 150% of the weight of the car? Oh, that's interesting. So where is the velocity vertical? Well, the velocity is vertical here. Here, the velocity is vertical, and the velocity vertical is here. Are these velocities the same? V1 and V2. Okay, are the speeds the same? The speeds are the same. Yes, thank you. Velocities are, of course, different. I'm sorry. But the speeds are the same. Yes. Modulus of V1 is equal to modulus of V2. They have to be conservation of energy. Of course, we're talking about a smooth track. Yeah, so I haven't mentioned that, but yeah, we assume it's a smooth track. Spherical horse in a vacuum. Right, so we need to find the acceleration. So it's sort of a trick question because when I do not specify which acceleration, and if I don't specify which acceleration, that means you need the total acceleration. Total acceleration. Because the total acceleration you already know, it consists of two. It consists of the gravitational it consists of the centripetal acceleration and the tangential acceleration. So let's label this points A and this point B. We know it's released from the minimum necessary height, so it's released from 2.5 mg, 2.5 r, and here it is a height of a single r. So for A, velocity at, let's call it velocity A, velocity B, velocity A, velocity B. Velocity at A, 1/2 mva squared, is the height from which, so you can find the difference in height. You don't need to necessarily go through all the trouble of, it's basically the same as if it rolled down from 1.5 r. So 1/2 mva squared is equal to mg 1.5 r. I hope that makes sense. Yeah. So we just assume it rolled down. We only need the difference in height. M cancels, and we have VA is equal to 3 GR, square root of 3 GR. And that's equal to VB as well. VB equals VA. Good. Right. Now at A, we have the car. Somehow, it looks to me that when I was 6, I drew cars better than now. They looked more realistic. Anyways, the force is acting on the cars, and so we have the mg. We have the normal reaction force. Normal reaction force. Let's call it NA, normal reaction at A. And that's it. Okay. So the centripetal acceleration, MAN, the normal acceleration, is equal to NA. And we know that it is mv squared over r equals the normal reaction at A. We're not looking for the normal reaction, are we? We're looking at the acceleration. So we don't need that. We just say then the normal acceleration. The normal acceleration is equal to v squared over r. Yeah, that's always true. So that's equal to 3gr over r. So it's 3g. Oh, that is surprising. Really? Normal acceleration is so big. Okay. And the tangential acceleration, because there's only one force acting vertically, well, it's equal to g. Right, this is the vertical acceleration. And since you have two accelerations, you have the normal acceleration, which is this. You have the normal acceleration, which is towards the center of this loop. And you have the tangential acceleration. So normal acceleration is 3g. You see, it's so hard to me to believe that A is 3g. I'm drawing it so short. So it's actually like this, and this is smaller. And this is equal to g. So you have acceleration. So acceleration is equal to the total acceleration is square root of 3 plus 1 g squared. So that's square root of 10 g. And the direction, well, the angle theta is arctan 1/3. So acceleration is square root of 10 g, and theta is arctan 1/3. And at B, of course, at B, and that's 3 point something times more than the weight, the weight of the car. So yeah, so B at B, so it's the same picture. AN, we have the car, we have the car, we have the car, and it has mg, and there's the normal reaction at B. And you can also see that we have the normal acceleration. Normal acceleration is v squared over r, and the tangential acceleration is g. Okay, and then and this is 3g as well. So acceleration at B, acceleration at A, acceleration at B is also square root of 10g. And the angle is also the same. So it's just this way. So we have the tangential acceleration and the normal acceleration. And this is square root of 10g. Great. Now, at what height is the normal reaction 150% of the weight of the car? And for this, we need to talk. So one of the questions in the assignment is about the aero sled. And this is sort of what we need to do. So we need to find what happens when the car is at an arbitrary angle. So let's say this is the center. And let's say the car is at an angle theta. The car is here at an angle theta. This is the normal reaction. So this is the car. And we look at the car. This wonderful drawing of my car. And there's the normal reaction force. There's the gravitational force. mg. And that's it. So we separate mg into components. So this is theta. And this is, so we have two components of mg. So this is mg cos theta. And this is mg sine theta. And as you can see, that it's accelerating this way. It's accelerating this way, so it's acceleration. The normal acceleration is this way. So ma normal is equal to n minus mg cos theta. So the normal reaction force. So no, that's not what we're looking for. We're looking for, well, and this is mv squared over r. mv squared over r equals n minus mg cos theta. That's the basis. That's the Newton's second law. So what do we not know? Well, we don't know the v, and we can work out v from conservation of energy. Okay, and we don't know theta, but theta is what we are looking for because we're actually looking at the height. So okay, so to find v, so conservation of energy, because to do the conservation energy, we need the height as well. So we need the height of the car above the ground. So this is the height. Let's call it small h. Small h. And the small h is equal to the radius minus r cos theta. If you don't believe me, try to work it out, because this is r cos theta. This is also r, so it's r minus r cos theta. So that's h. And we release it from height 2.5 r. So mg 2.5 r is equal to 1/2 mv squared plus 1/2 m G R 1 minus cos theta. That's the conservation of energy. So let's say the car is at point C. No, it's at point F. No, F is a bad point. Point D. At D. So GPE, gravitational potential energy at the top, is equal to the gravitational potential energy at D plus kinetic energy at D. All right, have I lost anyone? Is it? I hope it's not too confusing. So what we're doing is we use the conservation of energy. We use the conservation of energy to find the speed, of course, and the speed is this. So 1/2 mv. Oh, and cancels. I multiplied by 2 as well, just to make my life easier. So I have 5 gr is equal to v squared plus 2 gr 1 minus cos theta. So v is equal to 5 gr minus 2 gr 1 minus cos theta, which makes it 3 gr plus 2 gr cos theta, which makes it square root of gr 3 plus 2 cos theta. And that's the speed of the car. And now all we need is to put this in. So h is well, it's going to get a little bit messy. I'll risk it. I'll risk it. So I'm just going to put this into here. And I'm going to write down. So M. Oh, we know that this is 150% of mg. So it's 1.5 mg. So M v squared. So mgr 3 plus 2 cos theta divided by r. Okay. Is equal to n, which is 1.5 mg minus mg cos theta. And we have mg cancels. And oh, beautiful. 3 plus 2 cos theta is equal to 1.5 minus cos theta. It's actually very beautiful. 3 cos theta equal to minus 1.5. Cos theta is equal to minus 1/2. Theta is equal to 120 degrees. Ooh, that's beautiful. And the height is equal to r minus r multiplied by cos 120, which makes it r plus 1/2 r, which is 3 over 2 r, which is 1.5 r. Beautiful. Okay. I didn't have time to do this question beforehand. I'm just admiring. So somewhere here. So 3/4 of the way. So at a height of 1.5 r, the normal reaction force is going to be 1.5 mg. Everyone's gone very silent, and I hope that means you're just admiring the physics here, what we are doing. So going through, the hardest bit here is to do this. Yes, so the question. Yes, it works for more than 90 as well. Yeah, why not? Because there's no limitation here. We didn't assume that theta was a small angle. You have a very similar problem with the aerosled in your assignment, and then a couple more, I believe. So what you need to do is, oh yes, the ball rolling off a ball, of course. That's a beautiful one. So you have the ball rolling off. You have a conservation of energy. You need the forces. So there's the forces, and at some point n becomes 0 when it loses contact. If I am x high, will n equals x mg? What is n? Oh, I don't think so. No, I think it's a coincidence. It's a coincidence, but you can test this. It's a very nice. It's a very nice conjecture. I think no, because certainly at 2r, the normal reaction is going to be 0. And at 0r, normal reaction is going to be not going to be 0. So no, it doesn't work like that. It's a coincidence. Right. So, and now we are going to problem 3. A slide. So a slide is like a snow slide. So imagine you are going on a sled, right? A sled is going down a slide. It has the shape of an arc of a circle, radius 10 meters. The curved surface is smooth. The horizontal section has a coefficient of friction 0.15. How far will the sled travel if the acceleration at point A was g? Aha. So at A, the acceleration was g. What on earth does that mean? Because how could it be g? Well, g is the total acceleration. It's the total acceleration. And then we have two accelerations. We have acceleration towards the center, the normal acceleration. And we have the acceleration tangential, tau. Okay, so if you look at the forces at A, there's the gravitational force, which is down, mg. Then there's the normal reaction force, and there's no friction on there here. So these are the only two forces. And you can split them into components. So this is, so if this is alpha, then this is alpha. Yes, so this is alpha. So we have two components of mg. We have the component of mg cos alpha, and we have mg sine alpha. And the normal acceleration, so ma normal, is the normal acceleration is v squared over r. It's just a given. and the tangential acceleration is going to be g sine theta, g sine alpha. Okay. Now v squared. So we release. Just a second. I need to check something. Oops. Okay. Yeah. We don't know the height from which it was released, and I don't think we need to know. So the normal, we know that a normal squared plus a tau squared is equal to g, because that's what is given. The acceleration is equal to g. At point A, the acceleration was g. So that means the total acceleration, total is equal to g. And that's this. This is what we're saying. Okay. That means normal. A normal is a v squared over r. So square root of v to the power 4 over r squared plus a tau, so g squared sine squared alpha is equal to g. So v to the power 4 over r squared plus g squared sine squared alpha equals g squared. And the angle was 60 degrees, and sine of the angle, sine 60 is square root of 3 over 2. So we have 3/4. So v to the power 4 over r squared plus 3/4 g squared equals g squared. So v to the power 4 over r squared is equal to g squared over 4. We subtract 3/4. So what do we have here? So from here, we can work out the speed. The speed to the power 4 is equal to r squared g squared over 4. And that means that v squared is equal to rg over 2. Ooh, interesting. We don't, because we're going to use conservation of energy next, we don't need rg. So at point A, the velocity is rg over 2. Velocity squared is rg over 2. Okay. Using conservation of energy, so kinetic energy conservation of energy. Let's say the sled stops at point C. The sled stops at point C. So we have conservation of energy. We have kinetic energy at A plus gravitational potential energy at A is going to equal to the kinetic energy at B, and is going to equal to the thermal energy at C. Because it goes into heat, thermal energy at C. And we know that the thermal energy is the work done, which is equal to the work done. Now, it's the work done by friction. In other words, we can say kinetic energy at A, so it's 1/2 mVA squared, VA squared, plus gravitational potential energy at A. And we've already learned that the height, so the height is R minus R cos alpha plus mgr, 1 minus cos alpha. And that's equal to the work done by friction. The work done by friction is the force of friction times the distance traveled. Okay, so we have 1/2 mv squared. So v squared is rg over 2 plus mgr, and this is 60 degrees, so mgr multiplied by 1/2, because cos 60 is 1/2. So 1 minus 1/2 is 1/2, equals force of friction is mu mg, that's the force of friction, times the distance traveled. Okay, and beautifully, the mass in g cancels out. They're not zero, so we're allowed to divide them by them. So d, the distance traveled, is equal to r over 4 plus r over 2 divided by mu, which is 3r over 4 mu. And you can see that the units are consistent because that's radius, it's meters, and mu is unitless. Beautiful. So that is, the sled will travel 30 divided by 0.15 meters, which is 200, I believe. Be embarrassing. 30 divided by 0.15, 200 meters. Yes, the distance traveled by the sled is 200 meters. So yeah, the key thing is to work out, to look at here, is the total acceleration at point A. And total acceleration consists of two parts, of the tangential and the okay. I finished all my questions. Where is 4? I might have lost 4. Yes, thank you. 4 times 0.1 divided by 4 is 50 meters, of course. Thank you. Sorry. Any questions? Any questions that you'd like to ask? Pratham. So always use conservation of energy or resolve forces. Yes, start with the resolving forces and then conservation of energy to find the V. Yes, resolve forces, and you'll get an expression containing V squared because one of the forces is centripetal force. And centripetal force is mv squared over r. And then conveniently use conservation of energy, which has 1/2 mv squared, which is already present here. So that makes life easier. Do we need to add the arc length to the distance? No, because the friction starts at B. It's only the distance traveled from B to C. How far will the sled travel from B to C? Well, the arc length may be no. You could. Whereas as the sled decelerates, wouldn't mu decrease? Mu does not decrease. No, I mean the weight is modeled, so generally speaking, mu does not decrease. Empirically, we know that it doesn't, but in some rare cases, it can change. For example, if you had viscous drag changes with the speed. And the faster you go, the more drag you have. Is there a thing as elliptical acceleration? I have never come across this term, elliptical acceleration. What do you mean by elliptical acceleration? There's no such thing as circular acceleration. There's centripetal acceleration. Yeah. Well, okay. I'll leave it. I'll leave you here. I hope this was useful. I hope this shines some light on the way how to approach these harder questions on circular motion. And enjoy the rest of the assignment and the rest of your evening. See you, everyone. It says first for Monday. Okay, brilliant. That's always a pleasure.